Hello, good morning students. In earlier lectures we have seen the clock skew. Just we will have a little recap of whatever the things we have studied. What is the clock skew? Clock arrival of the clock at different times. Then reasons why, what are the different causes of clock skew. Then different sources of the clock skew. Then what is the skew in distribution. Then we have gone for distribution between these two. Then the major thing which we have to study today is a clock distribution technique, and in the previous class we stopped over there. We will go for a physical design. In physical design we have two different types of clock networks. One is H tree and another one is a balance tree. H tree is a regular structure which allows a predictable delay, and balance tree is a opposite approach of the synthesizing the layout based on the characteristic of a circuit to be clocked. You may say a grouping of certain elements, like that a balance tree is over there, and H tree is going to give you the regular structure. A H-shaped structure is over there. Now you can see from the figure also, you are going to apply the clock at the middle of the H, and whatever the flip-flops are being arranged, these are arranged at the edge of the H. Okay, you can here you can read over here one large central clock driver, quite obvious. Here you can see you are going to apply a clock to the center, hence you will need a large central driver. It is a recursive H-style structure to match the wire length. If you take an example, whatever may be the wire length at this edge, or whatever the wire length at this edge or at this edge, every wire length will be same from the source of the clock. The wire width will also get half at the branching point, and this is to reduce the reflection. Whatever the width of this wire, if there is any H tree at this edge also, the width will go on reducing, the width will become half. The wire adjusts the load capacitance. Buffers are being used to increase the drive capability, and skew increases with physical distance. If physical distance is more, the skew may increase, but this technique is going to have a physical design in such a way that the clock will reach to the all flip-flops simultaneously. Hence, try to reduce the skew as low as possible. This is the H tree type structure. Now we will see what are the problems associated with this also. Drawback to the original tree concept: the skew degradation along RC path. That is, a resistor and capacitors long wires are over there. That's why your wire are too much higher, and quite obvious you may get a skew if the flip-flop is located at the end edge of the H tree. Unrealistically large central driver. If you see the figure, you will come to know that you have to apply a very higher capacity driver at the middle of the H. Hence, the large central driver is being required, and non-uniform load distribution. Some flip-flops at the end may on, or some flip-flop at the end may not on. What you can do for this? Actually, the problem of a large central driver which is being required in this case, you can have another solution to this, that is introduce some intermediate buffers along the way. This is a buffered clock tree, and here in this region you can see for any such a clock, you have whatever the clock is going over there, you have edge buffers in all the directions. This is a west side edge buffer, this is the north side, this is south side, and this is the east side. And on every line you can apply the buffers, and you can avoid the central high capacity buffer. The advantages of buffered H tree: ideally zero skew, can be low power, low area, and cat tool friendly. Disadvantage: sensitive to the process variation and local clocking loads, inherently non-uniform. Another technique of clock distribution is a balanced tree. In the balanced tree, you can see that there are different clusters. You may say a balanced tree is some sort of a cluster based clocking. You can see the different clusters which are being shown in the figure, generated by placement and routing. These clusters are being generated by placement and routing. Clustering is used to guide a placement, and clocking tree is synthesized best on the skew information. Actually, whenever you will design a circuit, in that circuit, if you know that there is a certain section of your chip which has a skew, then for that particular section a separate clock is being given. This is actually the balance tree. Another technique is over there, which is a clock distribution tree. This is you can see a clock distribution tree. Initially the first clock is being taken from the same clock. The two clocks are being derived with the help of buffer, and from 2 the 4 clocks are being derived from by using the buffers, and similarly this is go on increasing. You may call it as a driver chain. This is a driver chain to drive the entire load from a single source point of a clock. From a single source point of a clock, you can have a driver chain which will drive the entire load or entire the flip-flops. There are different arrangements of clock are also there. This is the different clock tree styles. Okay, H tree model, binary tree model, fan out balance tree model, and spine and trunk model. This is a fishbone model, like that also are over there. Practical problems in clock tree synthesis. Okay, actually whenever you come across the chip design, clock distribution carries very important role, because synthesis of clock is very important, and most of the power is being dissipated in clock nowadays. Or in the circuits, your circuits are very less circuits are a combinational circuit, whereas you can say that all circuit which are using memory, or the circuits which are designed, all circuits are sequential and having clock. And if clock is over there, quite obvious the power dissipation related to the clock will also over there, and the routing of the clock to all the flip-flops is essential. That's why whenever you go for a clock tree also, okay, large size is over there due to SOC integration. The same thing I explained. Okay, unbalanced flip-flop distribution. It may happen that in the certain part of your chip there will be a larger flip-flop as compared to some another part. This may happen. Iteration cost is over there, test clock is over there, multiple clock frequencies are over there. Okay, these are the things which are being practical problems whenever you are synthesizing a clock tree. Now the last topic of today's lecture, that is the clock jitter. What actually the jitter is? Clock jitter, clock skew we have seen. Skew means what? The arrival to the flip-flop at different times, or the time difference between arrival at a flip-flop. And jitter is what? It is actually the difference between the time period of a clock. This is called as jitter. Means suppose that same clock has a different time periods, then it will give you the period jitter. Okay, it will give you the period jitter. Actually there are two different types. One is a period jitter and another one is a phase jitter, but I will not go in much more deeper of this. Rather rather what I will tell, that jitter is just a difference between the time period of the flip-flop, and this may happen because of uh, the source is not constant. Source may not, the component which are being used in the source of the clock are varying, and it will produce a jitter. Okay, maximum difference in the phase of a clock between any two periods is called as a jitter. The jitter type: period jitter and cycle to cycle jitter, phase jitter. Okay, thank you very much.